Maybe it is.
But definitely was a big reason I got interested in the area. So I have a lot of debt to Muriel. So, and I have no idea what the title of her talk is because she kept it private. So I'll let her tell us.
Thank you. Well, thank you very much, and thank you all for coming. Yes, I had a different talk which was on musings, and the musings were still too musing-like. So I think I used Ken as my guinea pig, and he was very kind, but I could tell by the facial expressions that he was not ready. So anyway, instead we're going to do this, but I'm very glad that I changed because I think it will provide a motif for the morning following Ken's talk and Nadia's talk. And this is where I show that, it does work. So here are my collaborators and some of the references of the papers that I'll be putting together. I'm really just trying to give some patterns that I think are interesting, at least to me right now, and I'm hoping they might be interesting to you, and I'm very glad that it's been so interactive, because I hope it will be interactive during this talk too, which means that if it's not interactive, my talk's really boring, but then we get lunch earlier, so there's there's a trade-off, but it's not all bad. Okay, so here's the setup for secrecy, which we saw. I don't have a really cool Alice and Bob like Nadia. I just have a base station. Alice and Bob, they're trying to talk to each other through a channel, and Alice is trying to send message X to Bob. Eve is observing message X, and of course what we're going to try to do is we're going to encrypt or hide message X using some function which is determined by a key. And then what Bob is going to do is he's going to invert that function given the key in order to recover y, in order to recover x from y, while at the same time we're going to of course try to make y be something which does not reveal much about x. So this is, but there's no noise right now. No, there's no noise. As a matter of fact, I'm not going to have noise, but be happy to talk about noise. The only noise will be from the presenter. So Eve should learn as little as possible about the message, and for the time being, we're going to call this as just the mutual information between x and y being less than epsilon. I haven't told you how long x is, how long y is. I haven't even told you why this might be an interesting metric or not, but let's go with that for the time being. Okay. So the questions, of course, are what can the adversary learn? How we design the cipher? How do we design this f, which is a function of a key, and what are some of the fundamental performance limits. Okay, so they're very different views in secrecy, and this is not news to anybody in the audience, but just to give a little bit of a sketch. In a very cartoonish fashion, you have the computer science approach, which is more around hardness assumptions and computationally bounded adversary, and obviously that has been extremely successful. And then we have the view, which I'm going to call information theoretic view, even though that's not entirely fair because there are many different views within information theory. But let's just say that if you go to ISIT and you look at most of the papers that have information theory and secrecy or security in their title, they will fall roughly within the, the philosophical framework of Wiener and the wiretap channel. Which is the picture that you saw before, and going back to what Ramon said, very often that picture has noise. And what you're trying to do, in effect, is trying to trade off the noise that the legitimate user sees versus the noise that the eavesdropper sees, and try to create codes which will work well below a certain threshold of noise and deliberately badly above a certain threshold of noise, so that the eavesdropper is not able to decode while the legitimate user is able to decode. In the extreme case, going back to the point of noise, what you're really doing is you're adding noise only to the eavesdropper, and the legitimate decoder has no noise. That's basically one extreme case that we're looking at here, but it all falls within the same framework. Okay, so there's been a long explanation on the connection among cryptography, coding theory, and information theoretic security, and there are more papers than can possibly fit in the slide. So these are just some few representative points. as I said, much of the information theoretic secrecy has come from the Wiener wiretap channel. There's been results over the last half a dozen years or so, sort of connecting that to coding theory. Maybe Moore's work belongs somewhat here, but in effect, creating codes that actually achieve these kinds of information theoretic secrecy metrics. Much of it has been looking at basically modifying traditional codes for communications over channels in order to make them have this kind of thresholding effect that I spoke about, where above a certain threshold of noise, they fail miserably on purpose, and below that threshold of noise, they work well. There's a penalty that has to be paid, of course. So there's been some very nice developments in this, particularly low-density parity check codes. Okay, so we've seen a lot of this. Again, there's a lot more work going on all the time. A lot of advances in this field. But just to again put the lay of the land, what you have in cryptography is demand for new security techniques and metrics. We're usually concerned in the information theoretic secrecy, not necessarily with just the demand for new security techniques, and I think the talk that Nadia gave very much falls in that category of trying to connect all three of these, but really coming from the demand. In this case, we generally tend to be concerned from the wiretap point of view with having a mutual information. Remember, I told you I'm being really sloppy. I'm just putting mutual information of X and Y, right? But I didn't tell you how big, the vector X was, or, not anything about the vector Y. Generally, what we're looking at is mutual information between a long input vector X, where so N is always going to be big, a long input vector Y, where this R corresponds to the rate at which I'm transmitting. And when there is noise, what happens here is this is the rate at which you can transmit over your channel. And what we're going to do here is because
normalizing by M, right?
We will in a second, so keep that in mind. That this is going to 0, and I'm being really sloppy about what I mean I'm going to 0, because as as Max just said, normally this is normalized by M, which is, people are looking at asymptotically getting no rate through, which we'll see why that's, while that's just a special case of what we can consider in general. And indeed, that's why I have two arrows, even though they correspond to two different things. If I am normalizing by N, and I didn't want to write everything in, then I have the wiretap. If I'm not normalizing by N, then I have the one-time pad. And if I want the one-time pad, generally the rate is, I'm not looking at noise, so the rate is 1. So it's a special case where the rate is 1. Okay, so the question is, what if we allow this not just to be 0, but to become less than some epsilon? Okay. The question is, can I have new metrics? And I think the talk that Nadia gave very much also falls philosophically within this framework. And also, what happens if I want to try to encrypt with keys that are small relative to the overall the size of my data? Which, of course, the one-time pad has a key which is of the same size as the original data. And then, can I go from this to practical coding techniques that will fulfill the kinds of demands that have generally been fulfilled by more traditional crypto techniques, or maybe marry the two? Okay, so here's the outline. I'm just going to provide some examples of information theoretic secrecy measures that can readily be achieved with existing codes. I'm going to start out with a very simple example, and then go to interpreting keys as list sizes. And then I'm going to end with a small caveat about assumptions, which is actually based on Ken's talk. So there will be, I hope, going sort of a full circle for the morning. Okay, so let me just talk a bit about the coding framework that I'm going to look at. I'm going to look, in general, at a linear coding framework which can subsist inside a network. Okay. And the coding framework that I will look at if I'm in general a network is that I'm going to have, say, you know what, I'm not going to do this because I'm just going to put. Okay, I'm not going to do this because I'm going to take the 10 minutes from there, the 10 minutes that we gave to Nadia. No, it's okay. I can come back to it later, but I'm not going to do it I'll just not. Okay, so let me start with the first example. And the reason I'm starting with this example is because it's very, very simple to illustrate what I mean by trying to connect these information theoretic notions with simple practical codes. So what's a conventional approach to hiding the data? I'm going to encrypt the packets, and then I'm going to encode those packets. Right, and I'm not talking about how I'm doing the encoding. It doesn't matter too much. Okay, that's what I would do. So the fact that I had an encoding, whether it be a source coding, whether it be a channel coding, is in effect really not related to how I do my encryption. Another approach would be, for instance, to protect the code itself. Okay, so I'm still able to take combinations on top of encrypted codes. Again, that was the part that I punted for brevity. But basically, what I'm going to do is consider that what I'm hiding is the code itself, and the randomness, or at least the a priori uniform or quasi-uniform distribution that I'm going to have is coming really in two forms. One is in the form of the coefficients in linear combinations. I'm going to use a random linear code, and I didn't give you the definition of it, given only to the sources and sinks. So I'm hiding how I'm doing a random code. Okay? And the other one is that the data is also random. So if the data is also random and it's not uniform, then I'm going to run into problems. I'll talk a little bit about that at the end of the talk. But the data here is being used as a key. So what we're doing is we're going to be taking linear mixtures of the data in such a way that the coefficients of which we're using for the linear mixtures are random. And I'm being sloppy because I didn't go over the last few slides. Okay. So protecting the code. So what can we do here? Well, we can show the following. I use random linear coding, which means that I'm going to be working over a fairly large field size, and over this large field size, I am going to choose my coefficients uniformly randomly. And I'm going to mix, for instance, different parts of the data in that way. And a general result for the mutual information between the payload, the actual data that I'm sending, and the encoding matrix is that I can get that mutual information to go to 0 with the size of the field. And I'll show you in a minute what it looks like. And moreover, if I restrict myself to invertible matrices, right, because not all my matrices may be invertible in terms of the matrix, which is the linear code, then I can achieve zero mutual information either between the payload and the encoding matrix, okay, or between the payload and the original information, but not both at the same time. Now, what's interesting here is that if I look at having zero mutual information between the payload and the encoding matrix, this actually tells me something about my ability to reuse the same code, right? If I have a linear code, that means I can reuse the linear code. And if I look also between the payload and the original information, that's what we usually look at. Right? So this is, let's say, the more traditional view that I'm not revealing anything about what I transmitted, about the plain text, and this is something slightly different, which tells me about the ability to reuse the matrix. So the mutual information, the payload, and respectively the original information or the encoding is going to tend to 0 with the size of the field. And let me actually show you this and then go back to the other slides. Actually, I should look at the time. Pardon?
12:50.
12:50. And they're waiting for us at...
Well, no. The QB starts 15 minutes late. So
I started, yeah, okay. So I'll go back to, let me sort of give a slightly shorter version, and then I can go back. I don't want us to miss lunch. Okay, so using random linear coding, again, I didn't define random linear coding, but it's uniform over a field size. The information between the payload, and I didn't define it because I skipped those slides, and A is the encoding matrix, which is defines a linear encoding over n symbols, is going to be of this, order n, log q sub q, where again the q was defined in a previous slide, which I jumped over, but I'm looking at f sub q as the field over which I'm working. So log of Q here is the number of bits required to represent any symbol given the field size that I'm working in. Right? And Q is the field size. So what you can see here is these different conditions according to whether the elements are chosen in FQ with or without 0, and there's some other conditions and other theorems that you can give, according to whether your matrix is invertible or not. But basically, what you see is, this is not a really big code. I mean, if you think of the kinds of codes you usually work on in algebraic codes, this is really not big at all. It's just a very moderate size code. Just a few bits code is already giving you a very, very good decrease in mutual information just by going up by a few bits. Now, of course, eventually, it's a diminishing return, but already at a point where you're very, very close to 0. Okay? The fact that this, of course, is dependent on n is normal, right? I mean, the more elements I have, the more it's going to be an issue. But the nice thing is that you get a nice decrease in Q. Okay? So the uncertainty is of the order of the coding coefficients if they are known and uniformly distributed, and if the data is uniformly distributed. So all this really relies on the uniformity of the coding coefficients and also the uniformity of the data that is underneath that. Okay, so why did we bring this up? So the reason for bringing this up is to say that, well, there's some very simple things that you can do here with respect to mixing, let's say, trivial codes. I mean, a random linear code is a very simple code, and encryption, which is of a different type than the usual because you're seeing this mutual information go to 0, but then you can get simple and easy results that come out of that. And just to give you some idea of what this does for you, this is the work that was done with Telefonica. What you can do is, for instance, you can take, say, a multi-resolution code. So if you look at something like, say, scalable video, you'll generally have 3 layers of video. And what I'm going to do is, I have this matrix A, which I'm using to encode for purposes of secrecy. What I'm going to do is here I'm showing that I'm locking. I'm using the key to lock this matrix. So basically, I have one coefficient which is hiding layer 1. I have another coefficient which is hiding layer 2. And I need layer 1 to determine layer 2, so I might as well put in another one here. And then I have another 3 coefficients to hide layer 3, because to get layer 3, if it's a multi-resolution code, I need layer 1 to get layer 2, and I need layer 2 to get layer 3. So that means I need to decode those. Okay? Now this one, for instance, suffers from a known plaintext attack. If I send a known plaintext, I could figure out the A's. Right? So you can imagine doing just a little bit of encryption on top of your linear code, and getting beyond this sort of plain text attack. But just to give you an idea of what this does, so we have 3 flavors. We have vanilla, strawberry, and chocolate. Chocolate is the best. Going back to the point that was made before by Nadia. But this is a comparison that was run by our collaborators at Telefonica, Alberto and Celuta. And here what you see is the size of the data to encrypt in terms of bytes. So this is just, of course, growing linearly with the number of bytes. And this is, for different packet sizes and short codes, 1 byte codes, and so some different parameters, how much data you have to encrypt, how much encryption there is going on here, because here you're just encrypting the coefficients. Okay, so what is this doing in effect is just giving you nice information theoretic results, which in practice are showing up as lessening of the encryption. Okay, all right. So what we did in the example that I just gave is we brought the encryption back to just having to guess, in effect, the coefficients. Right? So the coefficients were my key. It wasn't quite as good as having to guess the coefficients. That was the best that I could do. Because remember, my mutual information wasn't always 0. It was getting towards 0 in certain cases. But in effect, we got it to the point where I had to guess the coefficients as long as the data was itself uniformly distributed. All I had to do was guess the coefficients. And what we're going to do, and this is work that was really mainly with Flavia, and I gave the references at the beginning, so also with Linda Ziegler, Ken, and Mark, my student Mark. What we looked at is sort of extending that idea to see whether we could get other types of, more general types of results about having mutual information go to zero, and also results which connected the key size to some information, some information about the code. Okay, and that's really what we're going to do here. And what we're going to do to do this is we're going to introduce something called list source codes. Now, list decoding is something that's been around for a long time. List decoding is decoding to a list, where the usual decoding is decoding to a list of size 1. So in list decoding, I decode to a list of, obviously, of size larger than 1, and that's generally associated. But by the way, you should feel free to ask questions. I know I've been, trying to shorten time, but I'm now okay. So from now on, you can ask questions. That's the time has been made up. So what we're going to do here is to see whether we can do a list decoding, but with respect to source coding. Now, generally, people don't look at this in source coding, right? Because you say, why on earth would you source code to a size smaller? Why did you, as far as a distortion metric goes, it would be odd for me to source code to something where once I get the code, I have to go around and guess and guess and guess and guess. That's not that's not a sensible thing to do. So it's not something that people have looked at, not because they were lacking imagination, but because there would be no point other than security, I think, to look at list source codes. Okay, and within that, we're going to look at a somewhat different metric called symbol secrecy, and that goes back to the question that Max asked about, is there 1 over n, where we're going to sort of play with what we mean by that mutual information going to 0. Okay. Kind of, the example that I gave was just really an example to give the feel of what it means to look at these kinds of questions. So that's the reference. Okay, so let's go back to the system we have. We have Alice, we have Bob, we have Eve, and there is a key which should allow Bob to decode what Alice sent, and Eve only gets to see the coded version. And the best that we can hope for is 0 mutual information. Okay. So if we look at what happens in order to get a 0 mutual information in the one-time pad, the entropy of the source is the entropy of the key. And I have to guess as many bits as the source has in order to recover it. Right? I have a key which is basically as complicated as the source. Okay? And what we'd like to do is to characterize a non-perfect secrecy regime when encrypting with keys smaller than h of k, because the one-time pad is not practical. So remember, for instance, what we were doing the hiding the coefficients in the linear code, we were encrypting with coefficients from a matrix that was multiplying the original data, right? So we had to guess those coefficients rather than guess the original data. Okay, even though it was relying on the secrecy, the part of the secrecy was relying on the uniformity of the data. So it was not independent of the data, but it was of a smaller order. Okay. So as I mentioned, what we're going to do here is we're going to look at cases where the key is much smaller than the original data, which is generally the kind of encryption that people look at. And the question is, can I still give fundamental limits, realizing I'm not going to get to 0, because it's not the one-time pad. I'd like to get to something small. Okay. So, what was that? Okay, I pushed it. Okay, so insights from the one-time pad. So we do have insights from the one-time pad. So what happens in the one-time pad is I have a set of messages, and I'm mapping it to a ciphertext. And in this particular case, the size of the ciphertext and the size of the messages is going to be such that the key here that is being added is just basically adding something of the same length as this n, right? So imagine this is, random, uniformly ID distributed. I mean, suppose that these sequences are made of uniform ID bits, and these sequences are made of uniform ID bits. I sum them up, and basically there's zero mutual information between Y and X. There's also zero mutual information between Y and K. Of course, there's a mutual information between the two together. Remember the example that I gave you before? The same thing happened, right? I can't have zero mutual information between the output and both the code and the source. I can have the code or the source. Right? Same thing here. I can have zero mutual information between the output and the code, or zero mutual information between the output and the source, not together. Okay? But basically what I'm doing is I'm taking these messages, and there's a uniform mapping that's going from the messages to the ciphertext, and that's what this addition is doing. It's uniformly mapping from here to there. Right? So that's the key insight from the one-time pad. That's what my one-time pad is doing. If the key is small, the uncertainty of the adversary is not going to be this big. It's not going to be uniform mapping from the left to the right. I can't do that. So what I'd like to do is I'm going to create a code in such a way that this uncertainty is still going to be, that the mapping is still going to be, if you will, as spread out as I can, as uniform as I can. But I'm going to have a constraint because it can't be uniform over the entire set. I can't, because that would mean that I'd have really zero mutual information, and that would require my key and my data to have the same entropy. Make sense? I see happy faces, I see unhappy faces, but that might just be hunger, so. Okay. So what we're going to do is we're going to take this insight, so this is this source coded message, and I'm going to take my input, I'm going to put it to a list source code, which is going to give me an output. And now this NR, which usually the R is the rate associated, usually when we see NR in information theory, it's this rate associated with transmitting over a channel with the noise, going back to the point that Ramon had made. Here this rate is actually, I've shrunk, right? It's in effect my source code. So I went from instead of having, when I had the one-time pad, a set of possibilities here, which equals the set of possibilities here in terms of the size, I now have gone and done a shrinking, okay, where in effect I'm picking a message. There are different messages that are going to map to the same output after my list source coded message, which means that in effect the list source coding says that each of the code words maps to several source words. Okay, so that's why it's a list decoding. Okay, and in order to figure out which of these is the correct one, I need some auxiliary information, and this is going to be my secrecy. Okay, so this is going to give me enough information to resolve the list and retrieve the message. So you can see a few things right away. I want to get as little information as possible from which list I'm in, right? So before it was trivially achieved because it was uniform, so I got no information at all. Right? Now I'm getting an information because by looking this, I know which dark gray bag I'm in. So I want to have that give me as little information as possible. Okay? And moreover, this auxiliary information is really going to determine how secret I am. Right? Which is going to determine in some way how big are those dark gray eggs compared to the overall size of the alphabet. So CalX is usually the alphabet of the source. Okay? So that's going to depend here on the key. Okay, so this is going to be my key, and it's going to have a length, which in general, which is going to have a set of possibilities, which I'm going to call n prime. And this is going to be where my key comes in. My key is going to provide information, which is going to allow me to figure out which of the possibilities in the dark gray egg was the right possibility. So the size of the pre-image can be equal to the key and is dependent on the encryption method. Right? Yes?
Can this logic be extended to the distributed source coding concept where we have
A Sapir-Whorf approach?
Yeah,
Uh-huh.
because here what we are doing is we are actually extracting the key information from the set of messages we have at the source.
Yes.
But in distributed source coding, you have keyframes coming from another source and the frames you want to like decode from another source.
Yes.
So in that sort of scenario, how can this principle be implemented?
So I think that two parts of your question, let me separate them and then tell me if I'm doing it correctly. So one of the parts of your question is, can you extend this to a distributed source coding like Sapir-Whorf approach? And the other part of the question is, can I, so I think maybe there are two different questions. Could I consider the auxiliary information as being a secondary source?
Yes.
Okay, was it the first or the second that you were?
I mean, both are connected. Like
yes,
here.
they're connected. So let me start out with the second question. So there's been work certainly looking at the auxiliary information as a secondary source, right? There are two issues though. If you have the auxiliary information as a secondary source in a Sapir-Whorf setting, then you need to have rates for both of these. And what we'll see later in our definition of secrecy is that this may not have a rate. Right? So for instance, if I'm encrypting, for instance, Ken talked about DES, I don't get more bits with, if you will, in my encryption just because I used it more times, right? Maybe I should, and I should, be cycling through more keys, but in effect, that's a case where the key size remains fixed. Right? So if I'm using it in a Sapir-Whorf approach, and certainly people have looked in a Sapir-Whorf approach, then I have an auxiliary information which is somehow growing with this n, which may not be generally the case. So that's the answer to your second question. So let me try to answer your first question, which is I don't know. Okay, that is a good question. I have a guess that there's no reason in particular why this list decoding could not be generalized to distributed source coding, just because the techniques we use, which we'll see as random codes, and then we'll sort of implement it with MDS codes, are inherently not different with distributed source coding than with a single source. So I would assume that might be possible. So that's a really good possibility for extensions, but it's I don't know. Okay. All right, good. That's a good question. Yes, 10 minutes? Yeah, okay. So basically, what this is doing is it subsumes the deterministic encryption in one-time paths. As I just mentioned, in the case of deterministic encryption, this is just a fixed n prime here, right? I just have the size of the key, and however many times I use it. And in the one-time path, the n prime and the n are the same. Okay, so we like to look at things that are in between. And of course, in the Sapir-Whorf interpretation of secrecy, the n prime is not the same as the n, but it's of the same. It grows with it. They both grow together. So let's look at a fundamental bound for this source code. So let's give a formal definition. So I have my x. Actually, it's still not a formal definition. It's still a definition by picture, but it's a formal picture definition. So I have my x, which is brought out of my alphabet, because that's the only place I have for picking my x. I'm sending it through my f, which remember is the function I'm using to obfuscate, and out of this comes a y and r, and basically here I have 2 to the nr possibilities. Let's just say that y is over a binary alphabet, and in order to decode, what I'm going to do is I'm first going to apply a g, which does not actually invert the f. It inverts it as far as I can, which means that I'm inverting it to a list size. Okay? And I'm going to have an error if I don't get what I had sent. Okay? And the fundamental bound for the list source code is going to be the following. So this is this is the theorem, and it's very short. I'm going to be looking at how the length. So this is L. This is the size of my list. Okay, it's sometimes called the length of the list. I'm going to look at how the length of the size of the list relates to the entropy of the source. Okay, and of course my CalX, my initial alphabet. And basically, this is what you get, and I mean, it's sort of the kind of thing that you just stare at for a little bit. You have the rate there on the abscissa, and over here, I get to the point where, I'm just mapping into a single thing. Okay, it's a traditional source coding, and I get to h of x as well. I should. Okay, this is the case where the rate is 0. Okay, so this is basically, it's just whatever my entropy was originally, but of course it has to be normalized by the number of possibilities. So it's linear. It's very simple. Right? Very, very simple. And so you look at this and you go, okay, well, this is my rate. But what does this actually say with respect to the secrecy that's underlying it, right? So we have a notion that the secrecy is going to be somehow related to this list, okay? And I have the two extreme points are, trivial, and it's nice that have this linear relation in between. But what does this actually mean with respect to traditional secrecy when secrecy measures, and also maybe can we extend the secrecy measure? So what we're going to do is we're going to have a very simple, I call it a new information theoretic metric for securities. It's really a little too fancy for what it is. Okay, let's just say it's a simple extension of traditional information theoretic metrics. Okay, so I call it new. It's just, like I said, it's a slight extension. But we're going to call this symbol secrecy, and you'll see why in a minute. So the question is, what can Eve learn about individual symbols? In the one-time pad, you can't learn anything. Okay, when you're looking at a wiretap type of system, what you're saying is not that you can't learn anything about certain individual symbols, but on average, you don't learn anything. Right? So it doesn't tell you anything about specific symbols or even a finite number of symbols. It just tells you that if the number of symbols I'm considering is growing with n, right, that is going to 0. So it falls within our usual metrics. Okay? But here I'm allowing anything between any old symbol or a number of symbols that's growing linearly with the original vector. Okay. So the question is, what is the largest value, mu, such that for any fraction of mu symbols, Eve learns on average at most epsilon bits? That's what I'm going to ask. Right? And you can see how this connects to both to the one-time pad and to the case where it's just a given fraction. Right? All right. So here's a definition of symbol secrecy and a fundamental bound. So I'm going to be looking at the maximum, okay, I'm going to look at the mutual information between any subset cal I out of the initial symbols, okay, where I'm fixing the size of cal I, the cardinal cal I, to be t, okay, and I want this to be less than some n epsilon, okay, and I'm looking at the ratio of t over n. So if t is growing with n, then what do we have? With, pardon? Okay, if t is growing in n, we have a Wiener wiretap channel, right? I'm looking at the 1 over n is going as epsilon, right? So it's a case that the Max had pointed out before, right? Is everybody? Anyway, it's right before lunch. Everybody happy with that? Right. And what do I have if I have the one-time pad? Pardon?
T is not going with it?
Very good, Ramon. That's right. And then I can have anything in between. So T could be going, say, a square root of n, right, which is neither one-time pad nor the traditional wiretap channel. So anything in between. Okay. Does that make sense? All right. So this is the epsilon secrecy symbol. That's epsilon symbol secrecy that we call for a code n. And then this is what we can say. This is the theorem, which is really a corollary to the other theorem. Okay, so remember we had just a straight line. And the theorem is that this mu epsilon is going to be obviously greater than or equal to 0, but nicely and simply, upper bound by the min of 1 has to be no worse than 1, and L log of a cardinal of cal x over hx minus epsilon. Okay, so this L log of cal x and this hx really come from the previous theorem, and this epsilon is telling you just how sloppy you can be. So that's where the sloppiness comes in. Okay, I'm adding a little bit of slack. Okay? And if I look at mu 0, this makes sense given the previous theorem, right? So mu 0 is the case where I'm setting the epsilon exactly to 0. Let's see how it, yeah? Okay. How many minutes do I have? Sorry, I should have grabbed my phone.
Yeah, I think a couple.
Couple? Okay. So basically, at this point, what we're saying is, well, it makes sense. I have a secrecy measure, which is consistent with the secrecy measures I knew about. I have a very simple bound, which is very intuitive, which matches the bounds that I knew about in the extreme cases. And the question is there any way for me to achieve this? And it turns out, I'm going to punt this, and it turns out that you can actually get these achievable codes with a negligible small amount of error. And one of the ways of doing this is actually just to look at, for instance, use a random code. So if I use a random code to do my mapping, so I'm doing a mapping from using random codes from here to there. So remember what we did at the beginning, where I was talking about having a random matrix that was doing a mapping. In that case, the mapping was 1-to-1. I was just hiding the matrix. In this case, the mapping is no longer 1-to-1, but I am hiding the matrix. Right, so it's a generalization of the approach I showed you before. It turns out that this is achievable with, of course, asymptotically small probability of error. Okay, so at that point, I'll just leave it, and I'll just say one thing, which is, actually I'll say two things. One is bringing back something that Ken had mentioned in the morning of why would I want to use this? Okay, so one of the places where you might want to use this is actually you can use it to do trusted storage over untrusted networks. So for instance, you can use these list source codes to do trusted storage where you code over different networks, over different clouds, and as long as the attacker does not have access to more than a certain number of clouds, the attacker cannot reconstruct. And you can show that the attacker, basically by having access to more clouds, is reducing the size of his list, but cannot reduce the size of the list to 1 unless he has access to a certain critical number of clouds. So that's an interpretation where getting access to more clouds is the same as shrinking the size of your list. Okay. It turns out, by the way, that I don't have to use random codes, so you can use random codes as a feasibility result, but I can use traditional Reed-Solomon codes, or more generally any sort of Vandermonde matrix based codes. So read Solomon suffices to do this. You can prove this. So what I wanted to say now is reference Ken's work and Mark's work, and the reason is the following. As we went along, we always talked about the fact that the source was uniform, and then of course I had to have some sort of uniformity with respect to the the code. Okay, so uniformity with respect to the code was because the code, first of all, had to be difficult to guess, and also the code was trying to spread things out as uniformly as possible. Right, in the one-time pad, it was spreading completely uniformly. In the list source coding, what it was happening is that at least what we're doing is that in those initial eggs, right, within those eggs, things had to be mapped into those eggs as uniformly as possible. That's to say that I was not giving you any information about being in those dark-colored eggs beyond the fact that I was in a dark-colored egg. Right? It wasn't, for instance, that that everything in that egg was, a small Hamming distance away from each other. Otherwise, that wouldn't work. So, working off the results that Ken showed this morning, one of the things that came out of this was the fact, and he mentioned it, but I'm just going to put this up, it's great because he had already shown all the main results, that the assumption that we have a uniform distribution from the source is one that we often blindly used in information theory, particularly when we're looking at things like wiretap channels. And that assumption is often pawned off on the fact that I've done source coding. Okay. So I did source coding. In order to do source coding, I had to do a variety of things which generally made my input look uniform. And if my input wasn't looking uniform, I wasn't doing a good job doing source coding because somehow, I didn't get down to the entropy. And one of the justifications we give for this is, of course, the distribution of the typical set. So going back about the fact that all we know in information theory is the AEP. Maybe one or two more things, but fair enough. What's no? We can count on our fingers and toes, and when n is very large. But basically, if we look at the AEP, what happens is that we know that in the AEP, and again, this is coming full circle to Ken's talk, what we have is that the probability of a particular word is upper bounded by these two friendly endorphin-creating bounds. By this upper and lower bounded by these two familiar bounds. But it's somewhat different, actually, to consider the probability of a word in the typical set, picking a word in the typical set, given that you're in the typical set, and having the uniform distribution over the typical set. And it turns out, and this was the work that was presented at ISIT this past year, it turns out that these are different. Okay. So what does that mean for everything I said? Right. Remember, I was careful to go along and say if the uniform distribution is the initial distribution, but what does it mean? And the answer, and that's a little bit like the question that Anderson asked, what does that actually mean? Who knows? It doesn't mean anything good, that's for sure, right? It can't be helpful. Pardon?
Annoyance criteria. Yeah.
Exactly, so it's not good. Is it really bad? Not really clear, right? So, but maybe it also means that when we're looking at this list, it may be something different where you could look at a list with, successive guesses, right? So maybe the size of the list is not just the number of guesses that you would have to do to get to the right thing in the list. So anyway, so that's it, my conclusion. So just talked a little bit about different definitions of information theoretic security. I started out by giving you sort of a particular instance of a particular instance of those kinds of systems, and showing you that it does help, at least from a computational perspective. The performance often relies on uniform ID assumptions. That assumption is dubious, but in terms of the spirit of a workshop, we can really look at what can we say out of this. So one of it is, can I really look at different measures of some of the key entropies? What are the distributions of sources after source coding. I mean, some people have looked at this, but I think not so much from this perspective. And the other question is, should I be looking at my source coding with the purpose of giving me better uniformization? That's to say that maybe my source coding is doing fine from an average perspective. Just, it's a good source code. It's not sending a lot of bits that are useless, if that was my goal at the beginning. But maybe I could use a source code which is automatically also giving me better uniformization, which might be too much just from the point of view of trying to reduce my redundancy, but might be what I really need if I want to use it from a security perspective too. And now, lunch. Okay.
Thank you. We'll have to postpone questions as we run to lunch.
Yeah.